The maximum shear stress, or MSS theory, also referred to as the Guest or Tresca theory, predicts that yielding begins whenever the maximum shear stress in any element under loading equals or exceeds the maximum shear stress in a tensile test of the same material when it begins to yield. MSS theory was hypothesized based on the observations made from tensile tests, where the fracture lines form at approximately 45 degrees with the axis of tension. As discussed before, the shear stress is maximum at 45 degrees from the principal normal stress direction, or 90 degrees on the Moore's circle. Therefore, it is reasonable to assume that shearing is the mechanism of failure for ductile materials. Now let's consider a tensile test where the only stress component present is a normal stress, sigma. This will result in principal normal stresses of sigma 1 equals sigma, and sigma 2 and sigma 3 are both equal 0. And the maximum shear stress is calculated by sigma 1 minus sigma 3 divided by 2, which results in sigma over 2. At yield, we have a sigma equals Sy, which results in the maximum shear stress at yield equal to Sy divided by 2, a factor of safety formulated as the ratio of the maximum shear stress at yield divided by the maximum shear stress can now be stated as the following. Now, let's visualize the safe and failure regions predicted by the maximum shear stress theory. We plot a sigma A and sigma B on a set of axes and mark the material's yield strength on the axis. In the first quadrant, there are two possible cases. 1. Sigma A is larger than sigma B. This results in principal stresses of sigma 1 equals sigma A, sigma 2 equals sigma B, and sigma 3 equals 0. So the maximum shear stress becomes sigma A over 2. At yield, the maximum shear is Sy over 2. Equating these two results in sigma A equals Sy, which is our first failure line as shown in the figure. Similarly, we can do this for the second case in the first quadrant, where sigma B is larger than sigma A. Using the principal normal stresses, we can calculate the maximum shear stress as sigma B over 2. This results in the failure line of sigma B equals Syy. These two cases in the first quadrant result in a square-safe region as shown here. The fourth quadrant is an interesting one, so we'll discuss it next. In the fourth quadrant, sigma A is positive and sigma B is negative. This results in principal stresses of sigma 1 equals sigma A, sigma 2 equals 0, and sigma 3 equals sigma B. So the maximum shear stress becomes a sigma A minus sigma B divided by 2. At yield, we have this equals Sy divided by 2. Therefore, the failure line in the fourth quadrant becomes sigma A minus sigma B equals Sy. In the Cartesian xy coordinates, this represents the equation of an oblique line with a positive slope of 1. This failure line is plotted in the figure, resulting in a right triangle as the safe region. If we carry out the same analysis for the remaining two quadrants, we'll see that the second quadrant is similar to fourth, and the third quadrant is similar to first. Drawing their failure lines in this figure completes the safe region as an irregular hexagon.